A wide aerial view reveals the narrow land bridge between two oceans.
Engineers observe rivers, hills, and lowlands across the region. Water flow patterns shape early thinking. Nature sets the constraints.
This path along the ridge looks viable.
What about the water crossing at Sector 4?
We can bypass it using the secondary elevation line.
The sea level difference makes a direct passage impossible.
Then a controlled water system is necessary.
We can build the locks here.
Seasonal river flow is observed calmly over time. Water volume changes inform future planning. Long-term patterns matter more than short moments.
Survey teams move slowly across the landscape. Markers are placed to record elevation changes. Every step adds clarity.
See the difference here. Mostly large boulders and dense soil.
Right. We'll need the heavier equipment starting from that marker down. If we look at the green line, the elevation grade is sustainable.
And it offers the best balance for water control and overall distance. It's the right route.
If we reroute the water here, we can create the lift we need.
Yeah, instead of cutting through the ridge. That actually works. It completely reshapes the timeline.
A stepped waterway concept is refined. Ships will be raised and lowered gradually. The canal becomes a system, not a trench. Elevation differences are measured precisely. Gradual changes are favored over extreme cuts. Control replaces force. Small physical models demonstrate water movement. Channels, chambers, and flow paths are tested visually. Understanding improves through observation. Rainfall patterns are studied calmly. Water availability becomes an advantage, not a problem. Design adapts to climate.
The preferred route is adjusted section by section. Straight lines are avoided where terrain disagrees. Efficiency meets reality.
Clear entry and exit points are selected at both oceans. Natural harbors support the plan. The canal begins and ends with purpose. Existing rivers are incorporated into the system. Flow direction is guided, not blocked. Water remains active. Engineers consider daily canal use from the start. Maintenance and reliability influence design choices. Future operation shapes construction. The scale of earth and rock removal is estimated. Concrete needs are outlined broadly. Preparation replaces surprise. Paths, temporary routes are mapped across the terrain. Logistics supports construction. The selected canal route is marked clearly. Survey markers stretch across the land. The decision is complete.
Standing on this the future canal, the scale feels immense but achievable. Confidence remains measured.
Planning activity slows as execution approaches. Focus shifts from paper to land. The ground awaits change. Excavation tools and equipment are staged nearby. Everything is organized before movement begins. Order precedes action. The route is locked, methods selected, and systems defined. The project moves beyond ideas. Vegetation and loose material are cleared from the canal path. Ground visibility improves for precise work. Preparation creates control. Initial cuts define the canal's width. Straight edges guide further excavation. The canal corridor becomes visible.
Material is removed in planned stages. Each layer reveals different textures below. Progress remains steady. Removed earth is carried away along temporary routes. Movement flows continuously. Logistics supports momentum. Watch the topography adjust as we level the northern quadrant.
The gradient is stabilizing nicely. The high points are almost completely mitigated.
We've hit a dense layer here. The bucket isn't enough.
Adapt the excavation method. Bring in the breaker, but keep the pace controlled.
The canal route is divided into manageable sections. Each segment advances independently. Coordination keeps alignment consistent.
Depth markers guide excavation limits. The canal floor remains uniform. Accuracy matters early.
Temporary roads are formed alongside the cut. They support transport and movement. Access stays uninterrupted.
Small water channels appear in low areas. Flow is guided away calmly. Dry working surfaces are maintained. The turbulence decreases significantly as the width increases.
The laminar flow improves the navigation parameters.
From above, the excavation reveals its scale. The canal line stretches across the terrain. Progress becomes measurable.
We need to adjust the alignment slightly. See this discrepancy?
Yes. I'll move the prism pole 2 centimeters west.
Canal walls are shaped smoothly. Sharp irregularities are removed. Clean geometry improves reliability. Small natural features are redirected or integrated. The canal adapts without interruption. Continuity is preserved. Long stretches of open canal are now visible. The path begins to feel continuous. Direction is clearly defined.
Teams observe the excavation at rest. Measurements confirm steady advancement.
Planning and execution remain aligned.
Equipment is positioned for upcoming depth increases. Methods are reviewed calmly. The next phase approaches.
Multiple excavation zones operate simultaneously. Coordination keeps timelines aligned. Scale increases without confusion. Excavation nears planned depth in key sections. Targets are met gradually. Water management will follow.
Remaining loose material is cleared. The canal floor appears consistent. Earthwork nears completion.
Excavation activity slows across completed sections. Attention shifts to managing water flow. The project moves into its next phase. Excavation activity pauses across completed sections. Attention turns toward managing water paths. The project changes focus smoothly. Engineers observe how water naturally collects and flows. Low points and channels become reference guides. Nature informs the system. Existing rivers are mapped into the canal design. Flow directions are adjusted, not blocked. Water remains active and guided. Areas for controlled water storage are outlined. Boundaries are shaped by terrain. Future lakes are planned precisely. Large barriers begin to take shape across valleys. Their placement follows elevation logic. Water levels can now be managed. Edges of the new lakes are shaped carefully. Gentle slopes define stable boundaries. Water meets land smoothly. Water levels increase in controlled stages. Observations guide each adjustment. Balance remains the priority.
Channels link lakes to canal sections.
Flow paths are kept clear and direct. Continuity is preserved. The surface behavior confirms the design intent.
Agreed. Adjustments remain minimal.
Fine material settles naturally in calm zones. Clear water paths are maintained. Long-term clarity is supported.
The lake's surface appears calm and even. No visible disturbances affect shape. The system settles naturally.
The artificial lakes act as elevation buffers. They support gradual ship movement later. Water becomes the lifting medium.
Rainfall contributes steadily to lake volume. Natural input supports operation. Design works with climate.
Water is guided through different channels. Flow remains smooth and predictable. The system responds well. Lake edges are reinforced where necessary. Contours remain clean and controlled. Boundaries hold their shape. Levels across connected areas are compared. Minor adjustments ensure consistency. Equilibrium is achieved. From above, the lake's size becomes clear. The water body dominates the landscape. Its role feels central.
Lake edges align with planned lock locations. Transitions are clear and direct. The next system phase is prepared.
Routine observation becomes part of operations. Patterns remain steady over time. Reliability builds confidence. Water systems hold their intended levels. Boundaries remain intact. Construction can advance. Attention shifts from water storage to water movement control. Lock construction becomes the focus. The canal's core mechanism approaches.
Lock locations are marked beside the canal path. Elevation differences guide their placement. The system gains structure.
Ground is prepared beneath future lock chambers. Surfaces are leveled carefully. Precision begins at the base. Concrete placement follows a planned sequence. Layers build gradually. Uniformity remains visible.
Hidden water passages are formed within the structure. Paths remain clean and direct. Flow control is built in. Concrete surfaces are smoothed and refined. Edges remain crisp. The chambers take a finished shape.
Depth inside each lock is reviewed. Clearances are maintained evenly. Navigation space is assured.
Gate panels are set into their frames. They sit flush and balanced. Open and closed positions are defined.
Closures for gate movement are completed. Components remain protected and accessible. Operation stays orderly. Walkways form along lock edges. Movement paths remain clear. Observation is built into the design. Openings for controlled water entry are completed. Their placement ensures even distribution. Balance remains central.
Water enters the chamber gradually. Surface behavior is observed calmly. Responses match expectations.
Water exits the chamber through designated routes. Levels adjust evenly. The cycle completes cleanly. Adjacent chambers align precisely. Transitions between levels appear seamless. The system reads as one. Gate movement is reviewed in sequence. Openings and closures align with water levels. Coordination is confirmed. With water at rest, the chambers appear calm. No movement draws attention. Stability defines the scene.
This section here seems stable, but let's check the flow rate readings.
The sensors confirm everything is operating as designed. Accessibility is excellent.
Look at the flow rates here. The geometry seems sound for the water displacement.
Yes, the engineering holds up visually from this perspective.
Concrete surfaces appear consistent across chambers. No visual irregularities stand out. Finish quality holds.
Locks are observed through repeated cycles. Behavior remains predictable. Confidence grows. With gates closed, water remains still. Boundaries are respected. Separation is clear. Paths, platforms, and edges remain usable. Movement stays straightforward. Maintenance is anticipated.
All lock components appear complete. Nothing feels provisional. The system is prepared.
Water movement through the locks follows plan. Levels change without interruption. Operation feels smooth.
Final checks confirm readiness for regular use. No changes are required. Confidence remains steady.
Construction activity fades from view. The canal prepares for daily function. The final phase approaches.
All canal sections appear complete and connected. Water levels remain steady across zones. The system stands prepared.
With gates closed, water surfaces appear calm. Boundaries remain clearly defined. Control is evident through stillness.
Water levels adjust within the chamber. The vessel rises smoothly with the surface. Change feels effortless.
Gates ahead open calmly. The ship moves forward without interruption. Progress continues.
Markers and boundaries guide vessel movement. Alignment remains straightforward. Navigation feels intuitive.
The vessel enters locks on the opposite side. Water levels lower in controlled steps. The cycle mirrors ascent.
The ship reaches ocean level again. Transition completes without disruption. The concept proves effective.
Over time, operations remain consistent. Patterns repeat without variation. Stability is confirmed.
Over time, operations remain consistent. Patterns repeat without variation. Stability is confirmed.
Access paths allow routine inspection. Movement along structures remains easy. Care is built into the system.
The canal blends into daily global movement. It operates quietly in the background. Engineering supports continuity.
No redesign is required for operation. Original planning continues to perform. Time validates decisions. Between passages, water returns to stillness. Structures remain unchanged. Calm defines completion.
The Panama Canal stretches between two oceans. Earth, water, and structure work as one.